Hello everyone. Um, Welcome back to further day 4. So um, can you hear me?
Yes.
Okay, thank you. So let's start the today's session. It's for the day 4. So for the last 3 days, I think you explored qubits, entanglement, teleportation, and how machine learning models learn from data. So today's topic is the next logical step, how we multiple users or devices can learn together without ever sharing their private data. So this is called the federated learning, and later in the session we will see how quantum devices do this even more securely. So let me explain the practical example here. In imagine like yeah, you can imagine hospitals, let's say it want to build an AI model to detect cancer. So in here you can see two different types of federated learning. So in centralized approach, all hospitals send their patient data. Can you mute? Um, okay, thank you. So okay, let me explain. Then what I say here, you can see the centralized federated learning and quantum federated learning. In centralized approach, all hospitals send their patient data to one big server, and the server collects all data into one place. So then the AI model learns from these combined data sets at the end. In the centralized one, this is not the actually centralized one. So and the key point here is all data moves to one central server. The advantages here is that since everything in one place, it is easy to train. So, but this creates a problem, because hospitals must share private patient data. The transferring such as huge medical data is slow and expensive as well. And at the same time, if the central server is hacked, all patient data is exposed. So this is why centralized learning is risky in the critical applications like healthcare and autonomous vehicles, and there are lots of critical applications. So then now imagine hospitals want to train the same cancer detection model without sending any patient data. So at that scenario, we use this federated learning. Then in each hospital keeps that patient records inside the hospital. The hospital trains the model on its own patient data privately. Instead of sending the data back, they send only the model updates. So the central server combines all hospital updates and builds a much stronger global model at the end. This process happens for a number of rounds, for the optimizing or improving the hyperparameters that can provide much stronger and accurate model at the end. In here, this particular figure shows that simple example, the high level figure of the federated learning that I explain here. I think hope you got the idea what is the uh, federated learning here. So over the each of these iterations, what each client does is train their models using their own data and update their own model, which they download in previous round from the server as a copy of global model. And then they send only the updated weights to the server. Either whole model or the data will not be shared. Okay, so you can see here we can achieve a lot of advantages such as with this approach, no patient data ever leaves the hospital. Privacy is fully protected. Many hospitals can collaborate to improve the model. Even some hospitals may have a small data sets. So this is why federated learning is very popular for real-time critical applications like medical AI, autonomous vehicles, and fraud detections. Okay, for simplicity, let me explain in using this diagram. So it basically shows three steps in this diagram, but someone will say it has four steps. So let me explain here. This first is this step is client initialize model by retrieving a global model from the server. That means for the first round, it is the initial global model, which is not yet trained. And for the rest of the round, this is the model which we can consider as the latest version of the global model. So in the second step here, the local model training and upload is local training. And here each client trained their model using own data. And in the step three is sending back the client updates to the server. And finally, the server is responsible to aggregate one improved model. In quantum federated learning, so this is the example for the quantum federated learning. You can see in this figure. It involves the same idea, but using quantum computers. So quantum computers don't use normal numbers. They use quantum states, angles, and entanglement. Now you know all these quantum fundamental things. So in here, each client has a feature encoder, variation answers, and measurement steps. You know, in your quantum machine learning workshop, you got to know about all these things. So each client builds its own quantum model, and then instead of sending classical gradient, in this quantum federated learning, client can send rotation angles, circuit weights, quantum kernel features, or even teleported quantum states if you are using entanglement. So the service collects then parameters and perform quantum compatible aggregations. Like if the server receives rotation angle, so they can use angle away aggregation. So if sometimes the measure the fidelities, you can use the fidelity weighting combining. So and also if you use the teleportation, it is possible to use teleportation or aggregation and so on. So uh, this is similar to the classical Fed average, but Fed average and aggregation things, but respecting to the rules of quantum mechanics, we need to care about the quantum mechanics and quantum principles here. So that's the main difference of the classical federated learning and the quantum federated learning. So, and when it's come to the this slide that you can see here, why we need the quantum federated learning. In real situation, each client has different kinds of data. You know, we call it non-IDD data. So, classical federated learning struggles when data is very different across clients. So also, sending large classical models repeatedly causes communication bottlenecks as well. So classical models may have limited expressivity, and especially for the complexity, having the complexity of the data and the pattern. So then we need to have a better way to learn across distributed data. So this is the motivation for the QFL innovation. So because quantum states can encode much more information in fewer physical resources. So QFL becomes very effective. So quantum circuits naturally capture the complex patterns. You know how, because I think you got the idea about these things in yesterday workshop. So this is especially useful for the high dimensional or the strongly correlated data. For example, I can say the genomic data. So, and quantum models, the other advantage is the quantum models can explore certain landscapes more efficiently. Like, for example, that sometimes they can be work as a faster and converge or the generalized better than the classical models. Then these are the basic advantages, but the problem here is we have a question here as, is QFL always useful? Why we are having, if we are having the classical models and it's we can create them in a cheaper way, but why QFL needs, and is it available, and is it always useful? And actually not always, because quantum devices today are noisy. Noisy means it's consist with errors, decoherence, so, and also have limited qubits and have limited depth. That means shallow circuits. These days we have only shallow circuits, and so QFL is not magically better than every case because of these things. But QFL is useful in several key scenarios like critical uh, applications. Like QFL is most valuable when you need privacy, security, and complex data structure. So, um, and then the especially you can think it as the special key scenarios in the genomic, like the medical data and the autonomous data and the data applications where we need the most security, these things. So I think it's good to mute all. And okay, um, then the point that we need to understand here is we study QFL not because of this classical federated learning is bad, but because QFL prepares us for the next generation of AI, where we need security, high dimensional data, and quantum advantages. Uh, so the other thing here I highlighted here is classical federated learning is strong today, but it has limits tomorrow. That means? So classical federated learning struggles with very high dimensional data. I explained it previously, and also huge communication cost, and also the classical models sometimes cannot capture then some non-linear patterns. So the quantum models offer new mathematical structures that can overcome some of these limits. So the quantum is not replacing actually the classical, but it extends what classical cannot do. So the quantum machine learning normally, we know that it gives a QFL, especially QFL gives us access to the quantum advantage without sending this quantum data. Uh, pri- pri- Preserving the privacy. So the quantum machine learning, they normally need the quantum hardware, quantum memory, quantum communication, all those things. But when it's come to the QFL solves this by allowing clients to train locally and only send parameters. So even small, low noisy quantum devices can participate in real workload. So this creates a practical path for the quantum adoption. So that right now, that even the classical computers are cheaper, quantum computers are expensive. But this is the early stage, like that the classical computing in the 1950s or deep learning in 2010, it's early stage. So but people who learn early will lead the field when the technology mature. This is why the huge companies like IBM, Google, NASA, and some kind of pharmaceutical companies or banks and fraud detections companies are investing heavily on QML and also QFL. So then but the some problem will only be solvable with quantum and federated method. As I said, for example, I can say the genomic, drug discovery, and finance. In genomic, I can say there are patterns across the billions of DNA bases, which is extremely high dimensional. So the quantum state can represent complex correlation better. It's why now we use these things in the medical applications and medical research areas, which we are also undergoing in our research labs. So, and next the finance, in where we require real-time secure aggregation. So in that case, we need to have established the secure communication when we using the financial transactions. Now, then you can understand that using QFL today help to build complex model without requiring perfect quantum hardware, especially because of this distributed mechanism we used in the QFL, and also can begin with the hybrid quantum classical systems. But we can make the hybrid system by combining, integrating these classical and quantum details, quantum theories. So um, then the QFL, how we learn then if we simply say that the QFL is how we learn to combine AI, quantum, security, and also distributed system. So this is why we said that this is the combination of this that I said the AI, quantum security, and distributed system is the next generation of the intelligence system, I guess. So next, if I come to this one, it shows how the QFL implementation can improve. This is some of the examples that we are doing in our research, and also some of the global aggregation methods here I indicate here for you to understand. These are on a stage in the research stage because we are doing some of the experiments and using the different kinds of data to check whether these things are what the best method that we can use. But the main thing here is it's maybe the best options may be different from the different application perspectives. So we have to do lots of experiments for that. So this is for you to get to know about these things relatively the how the local training can be improved. This is one of method that I used these days. We our research lab is unfolding. So this unfolding and all the things are related to the classical, but we are trying to integrate it to the quantum world and quantum mechanics and to combine all the things. So this one shows the figure one, it's the QFF framework, as I said earlier. So in the figure two, this is the unfolded QFF framework. This is kind of a more advanced version. So, and in here, I shows here the quantum aware aggregation, some of the quantum aware aggregation rules, and also the classical rules. You know already these things, I guess. So these are special rules that create for the QFL because it is very different from the classical, but we want to aggregate. I mean that the aggregation parameters are totally different than the classical in the quantum when we come to the quantum. So in if I simply say about the angle aware, it's like quantum parameters. We take it as the rotation angle. So there we need to have the circular averaging. Sometimes it's very similar to the Fed average. When I show you some results, you will be able to see it. But sometimes it may be differed. But actually, and the reality is that the angle aware some is very effective than the Fed using the Fed average in quantum QFL. So in fidelity weighted means that clients with having like more efficient fidelity, the more fidelity weighted clients will have more weight. I mean, here weight means that they can have a more specified score for the aggregation process. So in the quantum kernel means it aggregates quantum kernel matrix, QSVZ that we use the quantum kernels and all the things. I hope you got the idea yesterday. So, and also entanglement aware means aggregation depends on the entanglement quality. In the other way, you can use the teleportation aware where you use the teleportation mechanics. These are not established yet, but I wanted to show you these things because it may be you can think of in different research perspectives these things. So these rules respect actually the physics of quantum systems, so they aggregate the quantum parameters correctly. That's why we are using these things in our research. So when it's come to the classical rules, these things work best for the classical models, but they do not fully understand quantum parameters. That's why we need specified quantum rules for the aggregation. Here, this is for you to see that how we can locally optimize our framework to train and to end up with the more efficient global model at the end, because uh, it is not enough to create the model and do the training and the optimization for the several iterations. We need to go for the hundred and thousands and lots of millions of iterations. If we can go for, sometimes we can get the good model, but sometimes we can have limitations for the resource limitations for the that kind of configuration. So then we have to think of like the ways to improve our model indifferently. So, for example, we can use some of the most efficient techniques for local training, like this way, the unfolding techniques is such kind of things. We are using the unfolding mechanism. So, if I simply say that it is a mechanism that we use, the individuals learn their hyperparameters. It's the mechanism of learning by learning. It's iteratively learn their model of hyperparameters. I think it has very deep configuration settings that I'm not going to explain all the things. Here you can see these methods give the higher accuracies than the normal general QFL method. So this is just for you to see. And then when we come to the QFL communication with teleportation, as I said earlier, and also I think you got to know the details about the teleportation and how we implement teleportation in between qubits. Here we need to use in QFL. If we use teleportation, we need to do it for the mm, parameters in where we weights. I mean, weights related to the model where we need to share in between the server and the clients. So when we share in these clients in between the communication, we can do the teleportations. So um, in the mm, in here you can see the classical circuit and also teleported circuit. This is just for you to see that I know you already know all the things. This is just a sample of the teleported circuit. I mean, in QFL, we need to have lots of parameters to teleport if you use the teleportation. So, and then this is the kind of the example that I want to show you with my demo. I have a demo that with combining with the toy examples for different kinds of aggregations, including this teleportation as well. But this is just the example, but I will show it that once you know that see that the demo, I will explain this one. So then classical Fed average, in previously I said the classical Fed average will be work for the aggregation, but quantum aware aggregation is significantly better. So in here you can see the example here. As I said earlier, Fed average and this angle aware should be in the on the same line, but actually this is not. This is, as I said, this is a toy example that I wanted to demo here. This is not exactly real result. So in the fidelity weighted and teleported aware method give high accuracy because they consider quantum angle geometry and reliability of each client and channel fidelity all. Then when it's come to the teleported aware, aggregation produces the strongest global model overall. That you can see the validation accuracy here just give the more accurate than the other two methods. So this approach is the best performing curve. So in the teleportation area, we use the model fidelity and also the channel fidelity, which means we use the teleportation quality. So this simulate the quantum communication system where that the some clients have better entangled, or some clients may have high noise and less noise channels, and so the good channels carry more reliable updates. That's why we take this the teleportation to give the weights for the each clients. So the bad clients at the same times get the low fidelity because they contribute less. So thus the teleportation aware aggregation becomes the strongest and most stable method. So but but you can have different kinds of another methods because these are not fully established in the QFL aggregation scenario. So in here, if you think what is the fidelity, I hope that you know the fidelity. Let me explain it simply. Its fidelity means the how close to quantum states. If you remember in data teleportation workshop, in if Alice sends a message to Bob using the quantum state, the uh, if the high fidelity, it means close to one, means the Bob receive almost exactly what Alice prepares. And if there is a low fidelity, we put it as a low fidelity, it means the close to zero. So Bob receive the distort, I mean noisy version of the Alice state, prepared state. So then the model fidelity measured. So the other thing is the model fidelity. So model fidelity, I mean the fidelity can be used, the model fidelity and the channel fidelity, as I said earlier, that what I use in the teleportation aware means here. So in model fidelity measure how good client's model is. Like in here we use approximate the validation accuracy and take the what the good accurate good accurate clients as the give you as the more higher weights here. And also the channel fidelity measure how good or noisy the content communication link. So in during the teleportation, in the entanglement sharing or the teleportation, you can use the channel fidelity. So these two methods combine in the teleportation of aggregation. So the client with better models and the clearer channels contribute more to the global model. So in this experiment, in here also you can see the how change these values in numerically. This experiment, the angle of aggregation produce same results as I said. This happens when client parameters do not wrap around the angle boundary. This is the circle is a mathematical option. So I think you can understand what is the angle boundary. So the classical averaging and circular averaging become identical. At that time, we get these kind of similar result. So in other data sets or the deeper circuits, the angle aware typically show benefits when rotations cross multiple periods. So that's the thing that I said. In real angle aware, it's sometimes show better result. So let me explain the demo now. I think it is good to go demo here because this is just for you to see that circuit efficient QFL happen here. This is one of our ongoing research which we use the deep unfolding and also the classical and quantum channel and how it's going on. This is just to see that I think I'm not going to go deep into this slide here. Now I wanted to show you the demo and just to show you um yeah, okay, just to show you the demonstration here. Here, this is the aggregation with QFL with the aggregation. I said that I used here the toy example for the some of the aggregation methods. So you can test these things, and also in your QFL task sheet, there are related things um, which related things I have used I shown here. I will show here, but you cannot uh, take as it is, but you need to specify the code as your task sheets because this is toy example. I would say so. In here I use these things, import statements that you need to import these Quiskit libraries. So then I here use the real-time data, transfer data. So and also this medemnis data for the pneumonia data sets. So I'm not going to go deep these things because these things not in here. I wanted to show you aggregation part. Basically, this is non-ID split here. So mm, the mainly I would say what we are doing here, we build a quantum neural network instead of quantum neural network or the QNN, you can use whatever the quantum model here, VQC, QSVC, whatever, for each client. So then we wrap it inside the PyTorch client. So in here we create the QNN, and then I have I will make this available for you, then you can understand, because I put all the comments here, you can understand what each line does. So we split data into the client, and each client runs locally, and then the server aggregates using these four different rules that I mentioned in the slides. So this is the QNN. You know how, I think you know how to create these things. So basic idea here is to give you the QFL idea. So this is the way that we use the QNN here, configurations for the QNN. So in the in here, what I need to show here is first thing. Sorry. Yeah. Here, as I said, I we use the torch given and we create the computers. This is in here. This is the part that we use the aggregation. So in the aggregation, we use four kind of methods here: the simple fed average, and then the angle average, and then the fidelity weighted average, and also the aggregate teleportation aware. And here, these are the simple code. This is simple code. You can make it complex if you use real-time teleportation on all the things. As I said earlier, I have defined predefined values for the fidelities here. Then, but in the real time, that you need to take actual fidelities, and you need to calculate the actual fidelities and take these things to give the weights for the specific clients based on the whatever method that you use. Okay, so I'm not going to give the each line by line explain here. So at the end, you can see the same results. So here in the federated round zero, and these are the results for the uh, four different kinds of aggregation methods. This is for the, I just used the only three clients and the four rounds. And at the end, I use this one I previously show you. And here, what the main thing that I need to say that importantly, because we use quantum sampling plus PyTorch federated learning, multiple layers of randomness. So then, therefore, the randomness are high here, randomness are involved. So we can reduce this randomness by fixing seeds, but I didn't do it here. But due to the floating point and sampling effect, even though we fix the seeds, small run-to-run variations also having the variations in the expected quantum machine learning results. Okay, because of the noisiness and then environment of the quantum, Qiskit will not give exactly same result at same time at different times. So but I want to say this because once you try to run this, you will see different result here, because this is toy example, this is not real example. So see this, once I earlier run, this gives this, and then I got this one, but the similar results there, mostly similar results there, but not exactly similar, right? So this is the major things that I wanted to share with you, basically about the QFL initial step of the QFL and the QFL aggregation. And I think that they will go deep into the QFL other things, because this is huge area. Then I would like to give this to carry on the Dave. So I would stop sharing. If you have any question, you can ask at the end. Dave?
Hello,
Yeah, you can go
can you hear me?
ahead, I think.
Oh, it's my turn.
Yeah,
Oh, okay.
yeah, yeah. Thank
All right, no problem. Hi everyone. Let me share my screen first. Okay. I hope you guys can see my screen.
Yeah, yes, there.
Okay, thank you. Okay, guys. I'm just gonna go through like how we might be able to like what are the things that we might want to have a careful setup experimentation, and I will try to touch on a few of the things like its challenges, something like that. Okay, so I'm pretty sure. Is there someone, anybody like have already tried the federated learning kind of thing before? Anybody?
Actually, no, sir. It is the first time I am seeing that one.
Okay, sure. Anybody have tried any federated learning before? Nobody else? Like, okay, all good. That's fine. So, federated learning basically, Sanika already explained in detail. I will also go into certain details here. Okay, so if you can see my screen. So we have a scenario here. Basically, we have a number of devices, right? This one is first device, second, third. At least we have three devices there. This may be in the different places. This can be in Dubai, or one could be in India, another could be in USA, right? So they are federated. They are in different places. Of course, they could be inside the same building also. It doesn't matter, right? So it's a bit different. At least they are in different. So they have a different kind of data. So you can see from here, this device has a different data sets. This device also have a different data sets, and this device also have a different data sets. But of course, we are not going to say that the data set will be totally different. There, this could be like images. They all have some certain kind of images for animals, like so, kind of some kind of the similarities there. But the level distribution, for example, maybe different. Like samples could be different, features could be different, right? And each device also has their model. Model, when you say model, basically classifier. That classifier will try to learn the patterns in the data sets. Like, okay, this animal has this kind of features, right? So it will try to say, okay, with these features, that the animal is this animal. So we are trying to do that in federated way. So basically, we are trying to have a machine learning, quantum machine learning in a federated version, right? So in different devices. So why is it so important? Because it's very hard. It will be very, very hard. Maybe nowadays the internet is super fast. Like it can transfer data from a few gigabytes to it's very fast, right? But still, we don't want to share data. One of the main reason because of privacy. Medical data, we don't want to share it. And it's also not necessary because federated learning has been proven very efficient in itself, right? So the federated version of quantum machine learning basically is quantum federated learning. So by default itself, certain level of privacy is already preserved because we are never sharing data sets. So data is never leaving the devices at all, right? So it will be there for. What are the things that we are sharing to the server? So there is someone who is trying to orchestrate, like coordinate maybe. There's something this person or this institute or this device would get the parameters that the model learned from that local device, and it would go to this person, and this person would average. Maybe there are so many methods. There can be you can invent another method also maybe, right? So that could be a good research problem. That is already a good research problem. Sanika is working on trying to find those kind of things. So so that's the thing. We and this person does something, averages the parameters, and it sends back to these all devices. So it will be same. When you're receiving, it will be different, but when you're sending, this that same parameters would be sent to the devices, and those devices would start training from those parameters now with the global new one, right? So that is how basic understanding of QFL also. Okay, it's almost similar to FL in terms of this, but inside. everything is different, right? We have a data encoding kind of thing, which is not in classical. So we have to change from classical to quantum space, right? So there are a number of devices. We train all the models locally, and by default, we have privacy preserved. Okay. So now let's see what are the many steps that you might need to have to perform the experiment for QFL. So there are these are basically some are basically a quantum machine learning thing itself. A lot of them are machine learning itself, but there are some added parameters and variables with federated approach, right? So first thing, data preparation. That is basically either you collect, either you use, or you get from somewhere out. You know, it's a data preparation, labeling, and so many things are there, right? It's one of the very important step. That data is split. We don't want to train on a small portion, or we don't want to train on everything, because we also need to test our models, right? How it performs on unseen data sets. Now, data distribution. Now it comes with the different from the centralized machine learning. We have to, just for the experimental purpose, we have to distribute data among clients. So there are approaches, and another is, do we need to have some form of dimension reduction? Do we need to make it smaller in terms of features? So that is that we need to decide. And another is scalar. Do we need to scale the data? Does it matter? So we have to answer that question. Another is, do we need to have IID or non-IID? What kind of uh, scenario we are trying to create, right? So that is there. How do we define number of clients, number of communications rounds, and what do you select for optimizers, local models? What kind of local models do you want to select? And how do you go about your training your model? What can be the aggregation protocols? And most importantly, what do you want to get from this experiment itself? What are the metrics that you are trying to show to your readers all right? So maybe accuracy or loss, or the other things can be there in terms of quantum federated learning. Circuit level results. Do you want to have a circuit level results, because it is still goes there, right? So, and yeah, do you want to use simulator or real hardware? Basically, it's some of these. Of course, there are a lot. QFL, it's so big. Everybody is working on different sections of QFL. It's not possible to cover everything here. So I've tried to cover almost overall things here. Okay, so in terms of data preparation, simple. If you have already done machine learning, this is the fundamental step. I just wanted to show it here. So let's take ATIS datasets, right? We can use it from sklearn datasets, right? And we can load that ATIS datasets. And so these kind of datasets are basically they are being prepared for us, to be honest, right? So we don't have to do much of processing in this kind of datasets. But there are certain datasets, like if you are doing for autonomous vehicles dataset, Waymo datasets, nuisance datasets, like you might have to. So depending upon what kind of datasets, for example, for this iris, we don't have to do much of the uh, data processing. So we extract features and labels, right? So how does it look like, right? So we have to know it first. Like we can get it from safe. Once we do that, we can see there are 150 samples, basically a table with the rows, right? Okay. And we have only 4 features, basically. Now you can also print the features here, and you can also print labels here. So in features, you can see it's basically numbers, right? So everything is kind of a number. So you can see this is 4, and related to that label is 0. So, and the labels are already in numerical format, You don't have to use label encoder kind of thing, or you can also keep it categorical. It's no problem with that. But yeah, it's good that it's already in a numerical form. The 0, 1, 2, 3 classes, either Satoshi, Color, or Virginia. So the three types of there, right? And the features are here like this. So we have just seen what is there already. Now comes scalar. Here we are using min max scalar. Why should you even try to use this kind of things, right? The data set should be already in the right format, right? But we try to do something here. For example, if you see in these features, they are in different range. 0.2, the lowest number, and to 5.1, it's the highest number. So in each, they could be a different, like, range. But we want to bring them to between 0 and 1. So you can see after we apply a min max scalar, you can see now they are in between. So all the values are like this. So it is believed, and it is also, you can do it yourself also. The accuracy is better with this kind of thing. Of course, it depends, might be, most probably it might definitely depend on different scenarios. But with these kind of things, the model, it makes easier for model to like classify, most probably. Okay, so that is min max scalar. We scale down the features. It's still 4. We haven't done anything. Now another is PCA. So when we say PCA, this is a principal component analysis. Suppose here we only have 4 features, right? We only have 4 features. Suppose if it had 200 features, what could happen, right? At the current scenario, we are using Qiskit, and it has a feature map protocols that is available. When we try to use it, the feature match is designed in such a way that we have to design based on number of qubits equal to number of features at the current scenario. So 200 features, 200 qubits. That would be really, really tough for the if we try to run the code and experiment, right? Very expensive computationally. So in that scenario, we have to apply PCA, dimension reduction, bring it down to less number of uh, features. There are other better alternatives. I have experimented with other ones. It's better than PCA, T, and I've seen something. There are others which are better, but yeah, it's up to you what you want to use according to your needs. So that's what you have to do. Again, data split. This is we are doing trend test split. This is done. Of course, you guys already know about machine learning thing. You already have that fundamental knowledge most probably. So we don't want to train in whole data, right? And we don't want to test on same data because there's no point, right? We want to test only on unseen data and train on like a more data so that our model actually learns and also performs, and we can verify its results. Now comes the part for our QFL experimentation, data distribution. Okay, so here I'm just tried now. There can be a number of ways. Okay, so of course there are a number of ways. Doesn't have to be this way, and so it's up to you how you want to distribute your data sets. Here I'm trying to just distribute that data, get the random indices, and then shuffle the data and split the data based on number of clients. We have 3 at the moment. So once we do that, we can print and we can see now we have distributed data for client 1, and it has its own label. Client 2, it has own feature and it has own label. Okay, it is only showing 3 samples as it is here. Of course, there could be more labels, right? Now, another point here is non-IID and IID. So you could have like labels. For example, if there was only this many labels, this is kind of you can create a IID or non-IID scenarios. Okay, one of the problem with federated learning, challenge with federated learning is heterogeneity, the data heterogeneity. And just to simply simulate that scenario, you can have that kind of distribution where you can have a like one device might have only few labels, right? So you could have that kind of distribution also. You can create and you can create that, make that scenario. Another important thing, sorry, is data size, right? Here with the iris data sets, our is only on the 150 sample. That is just 150. If we divide with two, three devices, we are only getting 50 samples each. But some devices, some data sets are not that, right? So some data sets are thousands. For example, genomics, it's I think 60,000 samples are there. So do you want to train on a whole data sets? It's very, very computationally complex. Like it takes a lot of times to just train, especially with these classifiers that we have. Okay, so it's up to you. The decision is up to you. You can take a small sample depending upon what you're trying to achieve with that experiment. Okay, so if you are trying to maybe accuracy, maybe more data sets, but if you're trying to compare different metrics, maybe you can have a small sample of data. So I'm not sure if there is a certain hard and fast rule, but yeah, so it's up to you how to choose the data size. And of course, it depends largely on what kind of tasks you are trying to achieve with the experiment and what you are trying to do, maybe classification or any other tasks, machine learning tasks, okay? And what type of data, as I've said, vehicular data, which I'm actually working on, just it's quite hard to process for the it takes some time, so it's very challenging for the Waymo data sets or nuisance data sets, right? You have to do a multiple of times, and data sets is huge. Even the okay, so it depends on what kind of data sets you are working on. Okay, and also how do you want to work on? It's up to you because you are the person who is trying to do the experiment, and we have to decide on ourselves what are the things we want to achieve from that experiment, right? So we can decide on that. We can decide on that thing. So that is a thing. The other thing is number of clients. So yeah, so I'm not sure if there is any hard and fast rules. Okay, you have to have this many number of clients. So yeah, so depending upon your need, if you have 1,000 clients for your experiment, it's going to take a lot of time. if if you multiply with the local iteration itself, right, it is going to take a lot of time, because if you just take one local iteration, maybe no, and if you take 100 local iteration, it will multiply by 100 into a number of devices, so it may take more. So depending upon that, you decide on how many number of clients you are. Yeah, normally we can see in literatures 10, 20, 50, 100, 200, even 1,000 clients, right? So in terms of number of communication rounds, how do we decide on that? So what is communication round? If you have never heard of federated learning, as I've asked, so as we said, it this device trends and it has parameters, models like numbers, matrix or something like. Let's say I'm just saying that, and it sends to this server. It receives from all the devices. It does something, averages, and sends back to this device. And then this device starts. So that's one communication round, right? So how many times do you want to do that, right? So it's also up to you. You can have 100 communication round. You can have 1,000 communication round. Okay. So it's up to you. Up to us actually. I'm also one of the students, researchers and stuff. So it's up to us, right? So and sometimes the reviewers might say, "Oh no, your communication are too many. Your clients is too many. You haven't proven your scalability. You have to use more number of clients." Right? Reviewers are doing that kind of comments. Reviewers always do that, right? So yeah, we have to decide. Too many, it may not be required. Once it reaches certain accuracy, we might never improve from there. So it's no point of running the communication around too many times, right? So it's no noise. But if we are running too less, statistically, that the result may be not good enough, right? So yeah, it depends. So number of communication round, number of clients. So we can decide on that depending upon requirements and what we want to find. And yes, what kind of ablation study you are trying to actually achieve. That is the main thing. Within this QFL framework also we can get a lot of results. I mean, we can work on different levels, like even its circuit level, like changing a few parameters, right? Changing the depth of the circuit itself for the local device. we can have a multitude of variations of results and experimentation within QFL. So of course, it's a big field. We cannot touch in every aspects. So yeah, we I think we can decide on where we want to work on. Okay. So yes, we have already covered this part. Here also you can choose what kind of every quantum classifier will have this part, at least as I've said here. So here, so feature map and the measurement. So yeah, so you can decide on which is good. The best way is to read some documentation from IBM itself or Qiskit machine learning. Please go to there. Okay. And also experiment with them itself, right? Try to run this, change these values, so we can change the values to 2 3 or layers, right? So yeah, these kind of things we can choose. One of the I think interesting is how deep should be the NZ, right? I think so. Official documentation says excessively deep might also not produce good results. So you see, so there are so many trade-offs, so many things, parameters we have to be careful on to get the a reliable result. Okay, so dimension reduction, feature matching, data encoding, what are we going to choose, how deep the our neural network, say quantum neural network, and that would be how deep should we use it, and number of qubits here. As I've said, as we are using Qiskit and with the feature map that we are using at the moment, I'm not aware of any other feature map. There could be, we are deciding the number of qubit based on number of features. So basically, if there is only 4 features, 4 qubits. From my experimental analysis, at least 7 8 qubits, it's okay. If you start going a bit more, maybe it could be still okay. Maybe 100 qubits, maybe a bit harder. I haven't done with maybe, so you can try it, those kind of things, and get a new result, right? And then okay, this is the problem here, and you can try to solve this. We can try to solve it and have a very productive research. And other is optimizer itself, right? There are a number of optimizers. Some are gradient free, gradient based. I would highly suggest, please uh, go through the documentation itself. They are well detailed, everything is there. And what I would do most of the time is I would go to the source itself. So just reading outside superficially is not enough, right? If you really want to dig deeper, so you can go to the source, or while you are importing in your code itself, you can right click here and it will take you to the source itself, right? I think you guys already know that part. So yeah, you can use different kind of optimizers. So this is also you have to select. And now comes the main part. So we have selected the data processing part, what kind of number of clients, and so many things are there, right? So the one of the important thing is what do you want to achieve, right? If you are trying to achieve classification, maybe you have to use a variational quantum classifier, neural network classifier. You can also use QCNN, or you can. There are other available ones, right? And in the Qiskit machine learning library itself. And of course, there is a good question to ask ourselves: is it possible for us to design ourselves, right, using the fundamental primitives code in the Qiskit itself, right? So not relying on the neural network that they have created. Maybe is there a way we could ask ourselves, to be honest, that question? So we need to decide on what we want to choose. And of course, if you are using VQC for this one, you have to we'll use uh, VQC for all. And the another problem would be, can we actually train one device with VQC, another device with QCNN, another device with neural network? That could be another problem, right? Research problem itself. So yeah, you can we can definitely dig on those kind of things. So is the client will have a quantum model to learn. Okay. Yeah, and please go through the documentation. They are way detailed. Quantum machine learning, Qiskit itself, they have official website. They are in IBM Learning also. There is a quite good resources. It's a very good resources, and you can try it yourself. So here is just a simple code snippet. I'm just trying to show it here. We created the J feature map. We are using real amplitude, and we are using backend as air simulator. You can use fake providers. You can directly run in a quantum hardware. That's you need to use generate preset pass manager. Okay, transpiler. We are using Kobila optimizer circuit. We have already done it. And here we have a sampler QNN. Okay, and this sampler QNN is going to here in neural network classifier. So whenever we are trying to fit model, we are going to call this object. Okay, now let's go to another. So here, yeah, now we are trying to create a client, number of clients here. Of course, you guys are most probably expert in programming itself. So this is one way. We are just looking to number of clients and adding those clients into this array, basically the object of those clients, right? The different array, and we are going to use those clients and call back. So basically, Python basic concept. We splitted the data set, right? We just want to assign to that particular client to that data set. So each client will have different data sets. And see this step here, you may not need it. So it depends on what you want trying to do. What I have done here is we are splitting the data set within the device itself, because we can have a training accuracy, we can have a training loss, and we can have a test, local test, like within the device itself, how the model performs, like after it trains, right? We can have, so the variations are, I think we can have a lot of variations, definitely. So yeah, it's up to us, we to explore, I think, right? And we have a classifier for each device, each client, and these are all the metrics or features. Like these are features, this is classifier, so that's for that particular client. Okay, now you might see it looks like we are creating a client, but it's just a simple formula. This is a TOE code. You can implement this one using TCP IP, right? A different client. You can use Arduino devices, run a different client from each devices. I mean, if you are even expert, you can use a mobile app and install in at least 10 devices and run the client and actually do the prototyping itself. That would be right. So yeah, there are other frameworks. I'm not sure about the QFL, but we have for classical federated learning, we already have a lot of frameworks. But you may be able to design that kind of framework if you're really into QFL later on, right? So there are a lot of I think plenty space to explore. So this is, we just created clients, assigned the local data sets. So yeah, I have a classifier, right? Okay. So now comes the training, model aggregation, what metrics that we want to achieve, and do you want to run on quantum hardware, sampler salts, etc. Okay. So basically, global weights, nothing is there. Then we train, we loop through communication rounds. Okay, we train the clients, and we store these are all the methods that's already available in Qiskit machine learning tutorial. If you search Qiskit machine learning, most probably you guys already explored those websites also. So these are just from using those ones. Okay, now this one is tricky. We are just using a math to average the matrices, arrays, or something like that. But can we come up with something more fitting to quantum federated learning, right? So that is a very open area. Most probably we can try to come up with the new methods. Okay, so we can work on that, and also trying to. So basically, what would happen is once it trains, it sends to the server, right? Of course, from the code's perspective, sorry, I have a message, I think. Just a Okay. I can't see the message. Okay, sorry. Anyway, I will. I have almost finished now. I'll just few couple of slides. So these are very interesting. These are like, now see, the code itself is like a one liner, right? So basically this will run sequentially. First this client will run, second client will run, third client will run. But in actual environment it doesn't happen like that, right? All the devices are independent. They can run anytime. All right, they can train anytime. They can train parallelly also. So to simulate those kind of things, you can most probably use thread. Okay, if you are interested, threading, TCP IP, as I've said, or actually devices, so you can simulate those kind of things. Okay, and at the current moment, of course, we don't have quantum computers accessible. We have to send that circuit that we are trying to run within this fit. Whenever we're calling this fit, actually, as I've said in the previous, everything with the circuit running, circuit being executed. So with this fit, sampler QNN, if you go to the actually source, you can see there is the circuit is being run. Okay, if you go deeper inside, you can see, okay, circuit is actually being executed, this kind of thing. And yeah, now if you need global accuracy, it's okay, you can get that. Or you, if you are happy with just the local training accuracy, that's done with this one. Okay, so yeah, so a little bit of steps here. And another important thing is you can also pass number of sorts. So yeah, there are a lot of customizations you can do. Okay, and here we see mode is backend. You can actually send it to quantum hardware itself. It will run, and we have done a couple of times. Of course, sometimes if you are not in queue, it takes a lot of time. But if it, the job actually to execute, it's very quick. You know, it takes 2 seconds, 15 seconds, 11 seconds, depending upon your sampler sorts. Okay, but yeah, but the queue is too much, so sometimes you have to wait, and I just cancel that and then run again, and some luckily uh, our jobs gets there. Okay, so those kind of things we can explore. So yes, depending upon what you want to achieve, here we can see results. In the first one, global test accuracy was around just 33%. Even the devices were performing so low, right? So uh, but as we go, as we move ahead to round 10, that accuracy is one. But yes, because for this experiment, I just removed the there were three classes, right? I removed one class and I just had two classes, so it's maybe too overfitting, right? The accuracy is too high, one. So maybe we have to go back and use another data sets. Okay, so and even the global is around within the four communication rate is one. And client zero performance, if we see test accuracy and train accuracy, we can see test accuracy is better than train accuracy, which is like, it's quite interesting. Yeah, test accuracy is better. It's quite interesting. Okay, within the local device itself. So we can see there is at least some convergence is there. Like we are accuracy is increasing, so it is working definitely. But it's but definitely one is too much, most probably. Okay, we might have to go back and do something and check. Okay, that was a bit setup for the QFL. Now around 7 minutes, I will conclude. I have only 2, 3 slides. Okay, I will just quickly touch superficially only this secured and efficient QFL. Okay, there are, see, QFL itself is a distributed environment. The clients are a bit far away. A server is there. You have to communicate. You have to send. Right. There is already a security threat. Right. You have to secure those model parameters maybe, or even the data sets when we are training it. Of course, feature mapping with the encoding thing with quantum federated learning, it's quite interesting. It have kind of privacy there, right? But of course, still we might want to secure data, right, using DP or any other mechanism, right? There are so many things. Security itself. Other thing challenges are we don't have the quantum essays. Like if we want to run on IBM quantum computer, it's expensive. You get 10 minutes free time, one thing. And if you are trying to run with more than 10 devices, each devices would have a local optimizer at least 50, then it is your whole 10 minutes is run out within a couple of at least even not even one communication round. So sometimes I used to keep like only one optimizer, like one step, so that's at least only one or two jobs gets created for each devices for each local iteration. So there are so many things with quantum federated learning, quantum machine learning itself. So okay, so that's the bottleneck. So we can control that, right? We just can wait for that. In terms of quantum infrastructure, yes, it's still in under development. Yes, everybody is trying to jump on quantum infrastructure, NVIDIA or Google, Microsoft, right? Big companies. But still, our UNSW, I think in Australia, they are also quite ahead on these kind of things. Yes, but still they are under development, and we have to rely on that. And so, yeah, our experiment is mostly at the moment simulation. So, simulators, air simulators, kind of things. Performance challenges. All the performance challenges that are like in classical FL, we can say in a way, of course, we'll come back to federated QFL also, right? Because it is still a distributed environment, and yes, there can be communication bottlenecks. And as you said, if I are trying to access a quantum computer, we have to send our circuit, go there, right, run on the quantum computer. And as I've said, you have to wait sometimes, and it's quite hard if you really are trying to experiment on quantum hardware. And it's expensive if we want to pay also. Some other challenges. I think this is the second last slide. Quantum computer development in the early stage. See, these are okay. These are old articles, sorry, nature paper. But yes, they are trying to say 100 qubits they cracked. I think yes, right. So yeah, they are trying to see. Okay, we have done this. This going on. One very interesting aspect is quantum internet. Okay, quantum internet basically we are relying classical communication, right? Basically, is it possible to have quantum internet just to be do a pure QFL, quantum data, quantum communication, quantum security, quantum machine learning, or even quantum optimizer? I'm not sure. Maybe I am saying that because I might sound stupid, but yeah, is it even possible? That could be another, I think, really interesting thing, open area. Of course, quantum noise and quantum errors are two big problems. People are trying to solve this problem a lot because of the inherent nature of quantum computers. This also affect on our experiment as well. So, what are the applications? I've just listed here. Any distributed network, basically, if they are trying to do some kind of quantum machine learning, can be applicable, right? Satellite, autonomous vehicle, or in the medical field, even quantum machine learning is have been like found to be very promising from chemistry. There are a lot of papers on that. So yes, applications wise, any distributed environment would be appropriate for QFL, and we all are definitely working together, right? So we hope there could be very promising research works in the future in the field of QFL and its application, trying to solve its challenges and everything. Okay, okay, guys. Thank you so much for listening to me. That's all from my side. I would like to hand over to Babo now. Okay, thank you.
Yeah, can you stop to share? Yeah. I hope you can see my screen clearly. So next part, I will cover the privacy in quantum federated learning and the different privacy methods to how to provide the protection for quantum federated learning. So first, we can say that why the privacy problem is very important in QFL. The first is that quantum algorithm. We know that on the client will run a quantum algorithm. we always say the quantum models. Quantum model are expect to process more and more sensitive data. That is because that based on the quantum parallelism. Quantum parallelism means that the ability of the quantum computer to involve a superposition of many inputs in a single unitary operation. That means any gate in the quantum circuit. So so the key part is the superposition of the quantum, the properties of the quantum. So quantum algorithm or quantum models are expect to have a high speed and to process more data than the machine learning. So that is the first reason. And the second is that we know that the quantum data cannot be cloned, but we can do many times of measurement to infer the real quantum state. And the third reason is that we can say quantum data is fundamentally different. So some classical protection methods may be not suitable for the quantum data. It includes some classical encryption schemes or some privacy guarantees cannot provide for the quantum models. So that's just said that some encryption scheme cannot be applied in the quantum models. Just say that some classical method cannot be applied successfully. So in the right side of this slide, we can see actually it's very common structure of the quantum federal learning, and there are several different adversaries in quantum federal learning. First is that we can assume the server is honest but curious. That means that aggregates as specified, but the servers try to infer the client data from the uploads. And the second adversary in quantum federal learning is that it is the malicious clients. It means that manipulate updates or queries to extract the information about the other clients. Means that these clients want to know other clients' data, or we can say that this client don't want a good performance on the global model. So sometimes the model parameters it upload is not right. So it's over large or over small. So it want to destroy the performance of the global model. And last one is that we can see the eavesdropper. Eavesdropper means that it can listen the classical or some quantum channels to get some informations. So that's three different type of the adversary in quantum federal learning. And next, we can see some private threats in quantum federal learning. The first is it can include some classical style threats. That means that these threats also applies in the federal learning. And we can also have some quantum specified Paris risk. The first is that from the classical side, we can have the inference attack, gradient inversion, membership inference, and the model poisoning. First, we can say that the difference between the membership inference and the inference attacks is that sometimes the model want to infer this data point is in the client's data set. For example, we can say if the model is trained on the A's data set. So if the personal data is in the A's data set, it means that the person not healthy, right? So in that case, we can use the membership inference. And the inference attacks, we can say that inference attack can cover the membership inference, and the inference attack can also infer other different attributes of the client's data set. And the gradient inversion means that we want to reconstruct the input from the shared gradients or the shared parameters of the variational quantum circuit. And the last is the model portion. It means that a malicious client sends the craft update to BS or backdoors of the quantum model. So actually, these three is similar to the last type of adversaries that shown in the last slide. And these three are about the classical size. And for the quantum specific Paris leak, we can say the first is from the encoding, because we know that in the classical part, the data don't have to encode on the qubit or on the other things, but the encoding, we can say it is a specific step in the quantum machine learning. So in these steps, the privacy leakage can appear. The next is circuit identifiability make easier evasion. So some research has shown that the symmetrical quantum circuit can create a higher risk of the model invasion. And the last is about EVs dropping. So that is in the same case that's shown in the last previous slides. And the next is there is many tools can help to provide the protection for the quantum federal learning. And one of the tools is quantum differential privacy. I have briefly introduced this concept in the one. And in today I will show some case how we can use the differential privacy mechanism to protect the privacy in the quantum federal learning. So you may be familiar with these figures. It says that the noise can from the two parts. One part, because the noise is a key component of the quantum differential privacy. Quantum differential privacy can provide or can utilize the quantum noise or the external noise to provide the privacy. So white noise can provide the privacy. If you are not familiar with the differential privacy, you can see this figure. So if, for example, if I ask your sensitive information, if I ask your age, and you think the age is your sensitive information, and you don't want to tell me your true age. So maybe your age is 20, and before you send the age to me, you will add a noise to it. The noise can be the positive one and also can be a negative one. So the answer sent to me may be the 19 or 21 or 22. So in this way, I cannot infer your real age, right? But if I want to know in a class, there are 50 students in a class, I want to know all the students' average age. So I can add each of the answer with a noise. But all the noise, the mean value of the noise is 0. That means some students provide the age with me with a positive answer, positive noise, and some provides the answer with me with the negative noise. So all the noise will, the sum of all the noise will close to 0. So I can't infer each of the students' real age, but I can know some answers on the behavior of all the students, such as the sum of the age, the average of the age. So that's just an example of how different privacy to provide the protection based on the adding of the noise. So this idea can also be applied in the quantum machine learning. That means that if you send the model parameter to me, or you send the model gradient to me, not the real gradients, not the real model parameters, but the parameters with some noise to provide the protection. So the difference between the federal learning and the quantum federal learning is that if we see the noise part, in the federal learning, the noise we have to add it. We have to add the external noise. So the noise may be from the Gauss distribution or the Laplace distribution. That's a different mechanism in the different privacy. But in the quantum federal learning, we can know that some noise are quantum internal noise. So this part of noise can provide the first layers of protection. And if we think the noise is not enough, it means that I won't have a higher level of privacy. We can also add some external noise, such as Gauss distribution or Laplace distribution. So if you want to provide the protection for the quantum federal learning beyond the internal noise, if you want to add the external noise, first you have to the right side you see is the step you have to choose. The first, you have to choose the mechanism to add noise, and the second, you have to choose the privacy budget. Privacy budget is a key parameters that's in the default privacy or quantum default privacy. If you remember it, we say the privacy budget is a value that the range is from the range is in most cases the range is from 0 to 1, because if the privacy budget is larger than 1, we say it can't provide enough protection for the personal data. So in most cases, or you can say in most research paper, the privacy budget is set from 0 to 1, and the lower privacy budget, it means the more noise we will add, and the higher privacy protection level we will provide. So the first thing is you have to choose which mechanism you have to use to add noise, and the second, you have to choose the level of protection you have to provide. So the second is based on the privacy budget, the value you have to choose. So next is that this is about if you want to use the quantum internal noise, you can use some channel noise or measurement noise. So actually, some papers are listed that how you can utilize this type of noise to provide the protection, and this paper provides the proof of the privacy budget. Here we see it is epsilon, the relationship between the epsilon, and here if you see it is about the depolarizing mechanism. So the important parameter in the depolarization mechanism is the possibility of the depolarization channel, of the depolarization noise, right? So here it means the P means that if the P is larger, more possibility of the depolarization noise will appear. And we say that if P is larger, more noise will be added, and the epsilon will be smaller. That means more noise and provide a larger protection level. So that is the equation, the formula of if you want to utilize the quantum default privacy and use the depolarization channel, you can use it. And in the right side, you can see actually this is a code to show how to add the depolarization noise. So it means that it can also not only apply in the quantum federal learning, you can apply in each of the model you want to add to provide the protection. And in this formula, you can see I will explain the different parameters. First, P is the depolarizing possibility, right? And here, the D is a Hilbert space. So it depends on the number of qubits you will use in the quantum system. If you use 2 qubits, the calculation of the D is 2 to the power of 2. That means it's 4. And if you use the qubits, the number of qubits is 4, the calculation is 2 to the power of 4. So that is the 16. So how to calculate the d2 to the power of the n? N means the number of qubits. And here, another parameter here is the smaller d. The smaller d actually is you can see here, it's the trace distance. The trace distance will measure the distinguishable of the two quantum states. So here, if you see in the formula, the lambda here, the lambda rho and the lambda sigma. The rho and the sigma is two different quantum states, and we want to calculate their trace distance between these two quantum states. So if you see this formula, it shows that the trace distance are the eigenvalues of the two different qubits. So you can calculate their trace distance and use it, replace the d here. So you can calculate the epsilon to prove how much protection the mechanism will provide to the model. So that is one way to provide the internal privacy. So we can say that we can also provide the privacy based on the external noise. So we can add some extra noise to provide more privacy protection for the quantum machine learning, quantum federal learning model. So the method, one of the method is the Gauss noise. We see the Gauss mechanisms. It not only applies in the quantum federal learning, it can also be used in the federal learning. So it is add a noise on the model parameters. So you can see that here we can add the Gauss random noise, or we see the Gauss random variables. And it follows that the distribution of the mean value is mu, and this is the standard deviation. So this formula is about the desensitivity Gauss values of this one. And if you want to use it to prove how much privacy the Gauss mechanism can provide, you can see this formula here. The delta is the sensitive. You can understand the sensitive as the difference between the model parameters you want to provide, or you can say it. Actually, the trace distance is the sensitive in the quantum circuit, in the quantum system. And here, the delta 2 is the sensitivity of the real values. And here, this is epsilon that's in the quantum differential privacy. And the delta is another parameters about in the differential privacy. It controls the smaller possibility of failures in the privacy guarantee. So in most cases, the delta is a very smaller values, such as the 0.01, 0.001. So, and here the sigma is how you can calculate it, and you can show the relationship between the epsilon and the sigma. So before you add the noise, you have to do another step before you add the noise is do the clip. So you have to clip the gradients and add the noise. Why we have to clip the gradient? There are several reasons. First, we have to bound the sensitivity. So how we can decided the sensitivity by the clip step. So if you set that the maximum of the clip values is 1, that means that the sensitivity is 1 times 2. That is because you have to calculate the absolute value, right? That means if the model parameters is larger than absolute value of 1, that will be clipped to 1. And the second reason is cap any client's influence. That means if the client is not a good client, it wants to upload a very large model parameters to destroy the global model. So you have to limit the influence, so you can use the clip step. And the last reason is that it can have a better robustness of the model. And yeah, I think I can show you the code of how we can add, because if you want to, if you want to add the internal noise, I think in the day one, you may have to know how to add the measurement noise, add the short noise, or add the declaration noise. It's maybe easier for you to add this quantum internal noise. So here I only show you how you can add the Gauss noise to the quantum feathered learning model. So I think most of the details of quantum feathered learning are covered by the dev. So we can quickly go through the first two block of the code. The first, here in this example, I also use the ATIS dataset. And here I only choose one label, 0 and 1, because the ATIS dataset actually have 3 types of the label, but it is an example. I only have the 2 type of label. And I split the train set and the test set, and the ratio is 80% for the train set and 20% for the test set. And next, I split the train set and test set to the client. So here I choose 3 clients. So I will split all the train data set and the test data set in 3 clients. And next, we can see that the feature map I choose here is the daily feature map. But for the quantum circuit, I choose another quantum circuit. You can also change it based on which one you prefer, or you can change several quantum circuit, or the quantum circuit can also use based on your preference, or you add a new quantum circuit designed by yourself to show which one have a better performance. And next, you can see this. I think these are also covered by dev, and I also initialize sample QNN. And last of that, I think this is important because this several piece of code shows how to add the Gauss noise to provide the protection. Here, the number of runs means for the each client model, the number of epochs for each model to training. This is the local metadata, sorry. The number of runs is about the feathered learning runs, and the local epoch is 5, I set here. And the clip value is 1, so the sensitivity here we say the delta 2 actually is 2 and the clip value is 1. It means that the model parameters, the absolute value of the model parameters, if larger than 1 or smaller than -1, it will be clipped to 1 or -1. Okay. Next is about the noise sigma. The noise sigma means that the amplitude of the noise we have to add on the model parameters in Gauss mechanism, and here is 0.05. And in the slides, you can also see if you have the sigma, you can calculate the epsilon based on the Gauss mechanism. So you can prove how much privacy this Gauss mechanism can provide for the quantum machine learning. And next is the initialize about the global with the global parameters of the global model. And next, we will train the local model. So for each of the sample QN, we'll add the classifier. And yeah, and then we will fix it. So next, this definition shows a clip update. So it means that if each of the parameters is smaller than C, we will directly return the data, right? And yeah, next you can say about, this one is about the client update. That means this is a local model parameters, and the global W is the global model parameters. So we will calculate the data first. That's the difference between the two different models. And based on the data, we will do the clip operation and add the noise based on the parameter noise sigma to add the ghost noise. And then so that in that case, each model will upload a noise quantum model to the server. So the server can't infer what's the real model, or can't infer what's the real gradient, can't infer which training data based on the noise, the gradient based on the noise model parameters. And next, you can do the evaluation. That means for the each federate round, we can test the accuracy. You can see now the accuracy is not stable, and the final performance is just 55%. That means because we add the noise. So you can also, in your task sheet, you can also change the noise sigma. In most cases, if the noise sigma is higher, so that means more noise we will add on each of the client model, and the test accuracy will be lower. So this is just the base code of the quantum feather learning, and how you can add noise on each of client model. You can adjust this basic model and do some variation for your task sheet. Yeah, I think, sorry, I think there still have last slides I have to present. Yeah. So last, I only want to conclude that the quantum default privacy is only one of the tools that can provide the privacy for the quantum model, or we say quantum feather learning. It is a good tool because it is very easy to apply, and the complexity is not high. It's a lightweight method. It is easy to add the noise, but in some case, when you add more noise, it means the model, the data utility, or the model performance will be lower. So in the quantum default privacy, the utility and the privacy balance is always a problem, even for the differential privacy. So how you can provide enough privacy, but achieve a good utility or achieve a good performance, it's still a task in this field. And besides the quantum default privacy, there also have another tools to protect the provide the protection for the quantum feather learning. The first is the secure aggregation, and the second, you know that the client may be upload not good quality model parameters. So from the client side, we may do the auditing process or to limited some performance or limited some operations of the client. And the third one is a text-aware training, that we can do some another step to avoid the attack, such as to the data augmentation. That means we may generate some sensitive data, or we can do some regulation or adversary training against the membership or attribute inference. The things we have to note is that quantum feather learning is very novel field. So maybe some classical methods cannot directly apply in the quantum feather learning, and still some researchers to focus on how to apply the classical one in the feather learning one. So some methods are still in the test and maybe cannot have a good performance. But if you are interested in this field, you can also try it for yourself. And in the right side, actually, is another method to provide the protection. So it's as the process of the encryption to do the secure aggregation. So if you're interested in this side, I just briefly introduce this. different methods. You can search some materials in the Google Scholar, or you can discuss with me. Yeah. Yeah, I think that's all the content for today. Yeah, let's see if some problem from your side.
I think one problem in the discussion forum, I think it's the Bao can answer it. Let me say it. The
Yeah,
Benjamin asked, yeah, if you can see the discussion forum, or
yeah,
do I need to repeat that question?
yeah. I say that download. And the meaning of this sentence is just say that uh, if the quantum circuit parameters can be inferred by the adversary, then the adversary can have the possibilities to infer the training points in the local data set. And if the quantum circuit is the we say if the quantum circuit I just say this is this page of the slides, and if the quantum circuit is symmetrical, that means it will be easier for the adversary to get the architecture of the quantum circuit, and it will be easier for the uh, adversary to infer the real data points in the database. And as this point is from I have read literature. I have read a paper, and this point is from a research paper. If you are interested, I will find it and send you the PDF of the research paper name so you can read it.
Yeah, that would be great. Thank you, Baba.
Um, yeah, in the discussion forum, sign up, saying uh, he got the wonderful time with this course, so it's good to hear. Thank you very much. So, and also he's asking that it is possible to contact you in the future if I need help. Yes, of course. If we can, if he time permits for our works, within our works, we can help you anytime. You can reach. I think it will be available in the future. Sometimes you will be able to, yeah, contact us in any way. I don't know the method. Yeah, sure. And anyone, do you have any problem? He's asking Navneet, is it possible to get the slides in PDF format? Uh, what we can say about that?
I think Navneet is not in the meeting.
Oh,
I'm not sure.
really?
Do you think we
Yeah.
can stop the recording or it should go on?
I think
Okay,
now,
all good. No problem. I haven't seen the
no,
message.
I think, but we need to start 9. So
Sure, sure. No problem. Okay, no problem.
yeah,
I think someone was raising the hand there. I'm not sure.
I don't see it.
I think Muskan was raising hand or something like that.
I think you will receive your
Hello, am I audible?
yeah, yeah. Go ahead. Go ahead, please, Muscat. Uh, now we can't hear you actually.
Hello.
Yeah, now we can hear.
So, uh, I have a question to the Dev. Like my question was when he was explaining, I guess slide 2 or 3. So
Yes,
at
yes,
there, at there you talk about the scalar. In scalar, the input was 4, but when you was using the min max scalar, so at that time this become 5. Like I noticed this in your slides. So may
yes.
you please like share your screen again?
Ah, okay, no problem. Just a sec. I have actually closed the slide itself. Okay, where is that slide? I think the first slide, I have to download it. Just a sec, just to make sure if it is the same slide. Okay, number. That's it. Yeah, please. Sorry, sorry. Just a week. Yeah. Okay. Is this the slide? This is the one, right?
Uh, no, actually, before this, there was a slide like,
Okay. Are you able to see my screen or
yes,
this one?
yes.
This one? This one, right?
No, after that.
Okay, this one?
Yes, yes, after that.
Yeah.
Your slide is not changing actually.
Okay. So I mean, yeah, you want to ask about min max scalar, right? Is
Yes,
that
there I see when when we're using like features, so at that time you give input 4, but after a certain of time, like yes, I guess this is the point where I noticed that after using min max scalar it become 5. Like when you see notice the array, so it is 0 1 2 3 4, but after using min max scalar it become 0 1 2 3 4 5, like one extra step, like one extra array. So why this is coming, like any extra additional input or something else, like any extra data? I'm confused too.
okay? Yeah, yeah. Thank you for asking that question. But which are you able to see my screen right now? Just to make sure, because the features will still be there. Like four will be still the four features with the
Yes,
min
I'm
max.
able to see your screen.
Yeah. So you are asking for this one, right? One, two, three, four.
Yes.
So yeah, the features will be still there, right? We had originally four features, like four characteristics of that particular data set, right? We only have three labels, but the features were only four. Now, when we apply that min-max scalar, what that
Hmm.
does is basically change the features values within the range 0 to 1.
Yes, I'm able to understand that range is changing, but I noticed that array size is also getting changed. Like
No,
first it was like 0 to 4, and now it is 0 to 5. That's my question.
no, the array size is still the same. Like this is 5.1, 3.5, 1.4, 0.2. Four digit, right? Four floats.
No, not
This
like
is
that.
oh,
Like here it
you
is.
mean the float decimals.
Uh, like first, if you notice, like I'm saying the first number of array, like in a single array there are four features, right? And after that there are like, you are using the four data set, like 5.1 is starting one, and then 4.9 for, I guess, 4.2 and 4.0 and 5, right? And when it is changing, so it becomes like 0.222, so I'm getting like 0.2 is converting to 0.222, and like that. But here if you see the numbers, so when you're in first image, it shows it's 0 to 4, but here it is 0 to 5, like I'm saying in regarding arrays.
I'm
Are you
really,
getting my point?
I'm really sorry, but you mean the like you say 5.1, 3.5, 1.4, 0.2.
Yes,
There are four,
yes,
right?
it is
Four
4.
features, four
Yes,
features, and here also 0.2222222 1,
yes, here
0.
also 4. But
0.6.
if you count the line, like in a single line there is 5.1, and in the another line, like in the another set of array, it is starting from 4.9. Okay, so if you count like this, so
Oh
here
no no,
is
you mean,
also
oh, you
an
mean, okay okay okay,
array
okay.
of array.
I think I understand what you mean. I'm sorry, that is actually the screenshot. So I have cropped it. Okay, I understood what you mean. Okay, you mean the rows, right? One, two, three, four, five, right?
Yes, yes,
And you are
yes.
saying one, two, three, four, five, six. There are 150 samples there. Okay, down there. You, I understand
Oh, sorry, I
now.
got confused in it. Like I
No, no,
was
sorry for
literally
that.
thinking like it is four, and here again it is four. So there
No,
should be
yeah.
the like four row and four columns. So now why it is like that?
There are
Okay.
150 altogether, 150. Okay.
Oh,
Okay,
now
I just
I get that.
okay. Sorry
Okay,
about that.
thank you for that. No,
No
no,
problem.
it was mistake by my side. And
No,
my
it's
another
okay.
question from you is like you mentioned about like in your slide non-IID. So I
Yes.
heard that non-IID are insecure. So is there any particular place that where we should use non-IID?
In that Muskan, right?
Yes.
In that regard, I'm not sure why non-ID would be insecure, but the one thing is about those data set is because their level distribution or their level is a bit different, so the performance would be affected. That is the main point with the non-IID. And the real world scenario that we are actually, it's actually a non-IID, and whatever experiment we are trying to do is similar to IID. So
Hmm.
there are a lot of works that are been done on FL to address data heterogeneity, non-IID. But in QFL, there are a few couple of works coming up, and you can try to work on that direction if you are interested. Also, data
Oh,
heterogeneity
okay.
problem. Okay.
Okay, thank you.
Thank you, Muskan. Thank you so much. Thank you for asking the question.
Okay, thank you for joining today. Today we are going to wind up. Hope you guys will connect to tomorrow with us for the last day. Okay, let me stop the recording.
Okay. Thank you, everyone.